Anyway, so basically what it's saying is, do you know what superposition is? Superposition means one thing is in the same place as the other. You know, superpositions for matter we think can't happen because they're in the same place at the same time. Okay? So they looked at the electron, they're like, what is going on? How can that electron go through one slit or both slits and still interfere with itself? So it's superimposed on itself. It's like this. You have this, my little wave thing here. Okay? Eyeballs up here. You okay? Oh. Okay, so I have a string. Particle, right? String, I can touch it, I can throw it. It's matter, right? But when I give it energy to get going here, it turns into a what? It's a wave. It's got wave-like motion, doesn't it? So this particle is now looking very much wave-like. And if I look at this wave that I've created from the string, where is this wave? Where's the string? Where's the string? Where, point to it, like the middle wave, point to where is it? Okay, it's there. I also see it down here. You see it down there? I see it over here. I see it down there. I see it definitely right here. And I see it everywhere in between as well. You see like that shadow that's in between them? Right? I see it, it's everywhere. It's everywhere in here but nowhere at all. It's up here at the top, right here. Down here at the bottom. How can it be there at the same time? I see a wave. I see a top and a bottom to the string. Do you? How can it be two places at once? How can it? It's not. It just appears to be that way. And when I say, okay, I want to find out where the string really is, I'm going to put it right here. What happens? The wave collapses and it goes back to acting like a string again. By my observation, by my observing where the string really is, collapses it, and that's where the string is. Look at it like a wave, it acts like a wave. Look at it like a particle, it acts like a particle. Okay? Hello. What are you doing over there today?
Separated salt.
Okay. But this is what we're talking about. The electron is in this place and that place and all those places at the same time. We really don't know where it is, and the act of looking for it tells us exactly where it is. Does that make sense? Yeah? So that's what they were looking at with this whole experiment, trying to find out where these electrons really are. But like I said, we don't know. What we're trying to do is this. Since we really don't know, the only thing we can do is figure out maybe a probability. Now I kind of like this slide. You observe me speeding. Are you familiar with the Heisenberg's uncertainty principle? Because according to the law of matter, or at least the law of Heisenberg, you can't know the position and the momentum, which is like speed included, of an object at the same time. So, in Heisenberg's theory, radar guns or laser guns don't work. But Heisenberg was talking about a very small particle, obviously not a car. So, okay, here's the history of the atom. You will need to know these 5 people, including Democritus. Okay? Start off with John Dalton. You don't have to know the dates. If I would look at these plus and minuses down here, what he added and what really wasn't happening. So John Dalton thought that the atom was a hard sphere that combined with other hard spheres to make new things. Thing is, he didn't know that the atom was really divisible, which it is. Then J.J. Thomson came up with his plum pudding model and said that it's a positive like ball of goo with little negative things embedded in it. Kind of like a chocolate chip cookie where the dough itself is positive and the chocolate chips are all the negative electrons. But Thomson was the first one to say the atom could be divided, which it can be. Then Ernest Rutherford came along with his nucleus. He said this positive stuff isn't all just everywhere. It's concentrated in the center of the atom. And the electrons just go around this nucleus in these orbitals, these paths. Then came along Niels Bohr, who said, okay, Rutherford, I give you the nucleus, and I give you the fact that electrons go around the nucleus. They just don't go in these elliptical orbits. They're in energy levels. Because if you look at this orbit, it's got a bunch of different energy levels it could go through. But these are concentric rings, where you have first energy level, second energy level, third. So he created these energy levels that the electrons are positioned on. Okay? And then finally here comes Erwin Schrödinger. Schrödinger said that these electrons are not, they are in energy levels, yes. But our finding them is probably very slim to none. What we have to do is look at the probability of where they might be found. Where might these electrons be? So he came up with probability modes, that they're going to be somewhere in some of these different locations in the atom. Just like if you come here after school looking for me, you come here because this is probably where you'll find me. But am I always here? No. But the greatest probability of finding me after school is in this room. Right? The greatest probability of finding electrons are in these different areas in the atom. So far, so good. Yes. Okay. Now this next video it's like a summary of everything. Do me a favor, please watch it, pay attention, and we'll talk about this when we get done.
Said that all matter and energy exists as both particles and waves.
And that goes for electrons, too.
Niels Bohr's classic model of the atom was familiar to science students everywhere. Electrons spinning around the nucleus like a tiny little solar system. And young scientist Werner Heisenberg didn't like models at all. He didn't even believe atoms were things. He thought of them more like a secret code.
If an atom can't be seen, it's not a meaningful concept. Your atom is boring, Niels Bohr.
Then, in 1926, Austrian physicist Erwin Schrödinger came up with a new atomic model that consisted of standing wave patterns around the nucleus.
I have found an equation that can be applied to any physical system in which the mathematical form of the energy is known.
So when Max Born came along with even more mad math skills, no one quite knew what to expect.
The wave function itself encodes all the information about the particles that can be determined through observation.
Right. In other words, using Max Born's equations, Bohr's orbits were now replaced with dark smudges where electron orbits might be found.
These are all the places the electron could be at this exact moment.
Born had found a way to reconcile particles and waves by introducing the concept of probability.
This is not probability due to ignorance. This probability is all we can ever know about an atomic system.
That's insane! What do you mean by probability? You're wrong, and I can prove it. Imagine for a moment sticking a cat in a box with a radioactive nucleus, which has a 50% chance of triggering a mechanism that will drop the hammer, breaking a flask of poisonous fumes, killing the cat. According to your matrix calculations, Max Born, the unobserved nucleus is a superposition, meaning it exists partly as decayed and also partly as undecayed. That's like saying the cat in the box is both dead and alive, which cannot be true. Ah!
Silly boy. Until the box is opened, the cat is both dead and alive. It's your act of observation that collapses the two quantum states into a single one.
Say what?
Open up the box and look inside.
It's alive.
100% alive. 0% dead. Your observation confirmed it.
Observation has always played a key role in science. Galileo spent his whole career demonstrating proper testing of theories through observation and measurements. But from now on, at least in the world of quantum mechanics, the very act of observing would have a direct effect on the thing observed.
Look at it as a wave, and it behaves as a wave. Look at it as a particle, and it behaves as a particle. I am now a believer of this new probability theory. In fact, I'll be so bold as to say that the description of any atomic state before observation is undefined. It has only the potentiality of certain values with certain probabilities.
And my uncertainty principle states that the more precisely the position of a particle is determined, the less precisely its momentum is known. So, it was no longer possible to say with any certainty that every cause had a clearly defined effect. But that was okay, because as time would tell, all sorts of things from transistor radios to atomic energy to space travel and microchips would prove that quantum physics actually worked, but that the only certainty in this quantum world was uncertainty itself.
Okay, and from that comes Schrodinger's famous cat. You know, Schrodinger's cat was the fact that the cat was both dead and alive. And with the cat being both dead, like how can a cat be both dead and alive? Well, the fact that you don't know. You know, I'm sure some of your parents probably feel this way when you're late coming home. You know, I know with my own child when she first got her driver's license and she was like 10 minutes late, I'm like, oh my gosh, she's dead. Oh no, she's fine. For about 10 minutes that she was late, I was fretting over dead or alive. You know, but when she walked through the door, 100% alive until I got my hands on her. That I was going to kill her, but no. But she's, but you never know. Until you open the box and look, you don't know if the cat is dead or alive. But you're opening the box. If you open the box 2 minutes later, the cat may have been dead. You don't know until you observe. Okay? So, that is the whole idea behind this atom. Until we find the electrons, we don't know where they are. But once we find them, they may not be there afterwards. So, it's all up to chance, probability. Now, our new model is called the quantum mechanical model of the atom. It's also called the wave mechanical model, because we talk about the electrons being waves. Schrodinger's model proposed that electrons are treated as waves. We need to treat them as waves. And with this wave comes the probability of where we're going to find these electrons. Okay? It's a probability. This is more than likely where these electrons are going to be found. Not that they are there, but the probability is greater that's where they're going to be. Okay? So the quantum mechanical model is our newest model, and it's what we know to be true up to this point. Okay? Just like the string, it's kind of hard to see the string here. This is just one big wave right here. So that string is anywhere between that top and that bottom. So basically anywhere in here I can find, let's call it the electron. But if I increase the frequency, now I've got two areas. The electron could be somewhere in here, or it could be somewhere in there. If I increase the frequency even more, Jackson, I will see there's 3 different areas where the electron can be. And the more I increase the frequency, the smaller the areas get. The more likely where I can find the electron in those different areas. Does that make sense? It's like this. Let's say I'm going to a Rolling Stones concert, and I'm like, Lexi, I hear you're going too. Why don't you say hi? Find me there and we'll say hi, and I'll buy you a soda. And me and 50,000 people. What's the likelihood of her finding me in those 50,000 people?
1 in 50,000.
Slim to none, right? Very, very, very unlikely that she's going to find me. But I said, okay, well, how about if you find me in section 432? There's only 10,000 people there. I've gone from 50,000 down to 10,000. Find me there. What's the likelihood of her finding me there? A little bit better, but still not very good, right? Yes? And I say, okay, well, forget that. I'm in row 11. Me and 200 of my closest friends. We're all in row 11. So now we're narrowing it down. So now she has to go through 200 people to find me. Right? But she's like, I still can't find you. Lexi, I am in seat 9. Okay? Now she knows where I'll be. Section 432, row 11, seat 9. Will I always be in seat 9? No. That's the greatest probability of where you're going to find me. But I won't always be there. I may go get some food, go to the restroom, stretch my legs, something like that, buy a t-shirt, but that's the highest probability of where I'll be. This is what we are now doing. This is how we're locating the atom. Oh, not the atom, sorry, the electron. Does that make sense? Yes? Okay, and when we locate the electron, this is what they look like. They've attached radioisotope trackers on here, Sean, and this is what we see when we look at the atom now. These are where the electrons actually are. These are the different areas. This is how the atom is broken up into the different areas. We still know that there are energy levels. We still know that N equals 1, N equals 2, N equals 3. We still have our energy levels, right? And we know that the lowest energy is closest to the nucleus. Yes? Okay. But here's where we start bringing things together. The first energy level is the first row of the periodic table. Sebastian? The second row is the second energy level. The third, the fourth. These indicate our energy levels. Okay? These energy levels are, we call rows or periods on the periodic table. Okay? They're called the principal quantum number. Now, here's the thing Bohr did not know. That these energy levels have sublevels in them. So, if we're looking at this, lights are coming on, and here's my nucleus. Here's my first energy level, N equals 1, N equals 2, N equals 3, etc. These have sublevels to them. The first energy level has only one sublevel, the level itself. The second energy level is broken up into two sublevels. The third energy level is broken up into three sublevels. What about the fourth energy level? How many sublevels would it have? 4. Fifth energy level will have 5. Okay? So the sublevel, the number of sublevels is equal to the energy level. So far, so good. Yes? Okay. This is what our sublevels look like. Okay? Our sublevels have different shapes to them. And these different shapes are sphere. We say S. The second one is a pi. That's why we use P. Then we also have D and F. These are the different shapes within our sublevels. Okay? Now, I'll show you this. this is what they look like. You won't have to know all these. Remember, the atom is three-dimensional, so they're on an X and a Y and a Z axis. Okay, Sean, if I see you sleeping again, you need to stand up, okay? I'm sorry, I know this isn't the most exciting, but you need to know this to do tomorrow. Okay? So please stay focused. So here's S. Here's my P. You have 3 different positions P can take. You have 5 different positions D can take. And you have 7 different positions F can take. These little lobes right here, like this lobe here and this lobe here, is where the electrons can possibly be found. Okay? So we have 2 electrons in here, 2 electrons here, 2 electrons here. They're somewhere in these shaded areas. Okay, Griffin? Okay? So we have all these different areas where electrons can possibly be found. Hey, hi.